Uh, we'll get started. So I just started a poll on the Python project. So request all of you to start voting on the quiz. Just want to get a general idea of where things are. And the first 10 minutes, I will be open to questions on the project. Anything that you are still stuck with, please let me know. And without giving you the full solution, I'll try my best to help you understand how you can proceed. So if there are any questions, can I see them? Please put them on the chat. We will review it and answer live. So feel free to put things on the chat. I'll start continue. So just a quick recap. We've successfully concluded the part 1 of our machine learning bootcamp, which basically was focused on learning the basics of Python programming. So we started with the first session, which was Python programming. We went through the basics using our Python notebook on Google Colab. Then last session, we went through the Python project, where I sort of walked you through some parts of the Python project. I believe it was Rohan who volunteered earlier. Thanks for doing that, Rohan, again. So we'll continue to do that sort of an interactive learning. I know that it can be quite intimidating to speak up in a classroom setting, but I want to encourage you that this is not your traditional classroom. This is a learning opportunity. So I really need you to voice your opinion here, and whatever you voice is not going to be used to judge you in any way. So please feel free to ask questions, pitch solutions, XYZ, so that we can have a very interactive session going forward as well. So now we are with this session. Today's session, we are going to start on the part 2, which is the what is called the traditional machine learning. Traditional machine learning, let me give a quick background on what is covered in this part 2, and then we'll go through what happens in this session. So in the traditional machine learning part 2, there will be 4 sessions. Specifically, the first one is the data science introduction, which is today. In the next session, we'll talk a little bit about ethics of data science and machine learning, because I believe that knowledge of a tool is not sufficient for us to put tools into good usage. There are some very fine lines of misusing or abusing data science, or even using it to make arrive at the wrong conclusions or misleading conclusions. So we'll have to we'll in this session, in the second session, we'll identify some of those pitfalls and see how we can try our best as data scientists, budding machine learning engineers, to flush out bugs early on. And then and in the third session of this part, which is on the 14th of March, we will step into what I call the traditional machine learning, which is dealing with structured data sets, which are in tabular formats. And this is where the learning algorithms start, which means you train a model, and now when you have a new example of input, you will be able to use the model to essentially do a prediction based on historical data that you have ingested into the training of the model. And then finally, we'll conclude this part with a mini project. And this mini project is going to be tied to what you have been working on in the Python project, which means as long as you've made progress in the Python project and you understand what is the problem that we are ultimately trying to solve, the mini project is going to help you make progress. So don't throw away any code that you've written in assignments or classroom or in your projects. You'll be reusing some snippets of code, and we'll figure out how to do that. Continue building on towards the final project. So with that, we'll get started with today's session. If there are any questions, please let us know. If you just joined the classroom, please vote on the quiz that you see here, which is basically just to understand where different folks are with respect to the Python project. and we'll get started. So if you see data science, which is today, there is classroom that is active. The take home is not yet active. I will launch the take home likely by tomorrow afternoon, so roughly within the next 24 hours. But the classroom itself is going to be valuable for us to get started. So I encourage everyone to click the classroom button. That should take you to the GitHub location of this new Python notebook, and then let's get started. So let me know when you can see my notebook. Can I get some thumbs up if you can see my notebook? Perfect. Thank you. Okay, perfect. So everyone has their notebook going. Make sure your Google Colab is connected. You know the drill. And now you have your new data science introduction notebook. So I do mention like a generic definition, data science is essentially the science of extracting useful information from raw data. And it is an interdisciplinary field, which means we use statistics, mathematics, algorithms, machine learning, scientific computing and visualization, processing, and systems. So data science is a very, very diverse field. And I would argue that the title of a data scientist actually can have different facets and perspectives depending on what your narrow specialization is within the context of data science. And I think you may have heard of this. Lots of media, they sort of over romanticize the idea of data scientists. They call it the sexiest job of the 21st century. While that is necessarily that may not be necessarily true, but I would still argue that this is one of the most important job functions that the present generation of engineers are doing across the world. And this is going to grow probably by a couple of orders as we go deeper into applying data science to multiple industries. So today, we've seen it get applied to social media, to agriculture, and from semiconductors to cosmology and more, right? So that tells you that regardless of what your industry interests are, right, based on your major, you will always be able to apply the principles of data science in order to help derive insights, in order to make decisions better. And data science is also inevitably going to be part of what we call the decision science, which means how do we make decisions as individuals, as organizations, as entities, and so on, right? So that is going to be a key part. And today's learning goal is to basically understand the basics of data science. Again, this is a boot camp, so we're not going to go deep dive into the theory behind it, but we'll try to go through some of the key concepts. I've recommended 3 additional readings here. Wikipedia, there's an open source, open access textbook that I found really, really wonderfully done. I encourage all of you to go through that book, make it part of your digital library. And then I've also linked a data science glossary. I think it's a collection of about 250 terms related to data science. You don't have to memorize all of them, but whenever you get a doubt, please feel free to go back to this glossary. So before we get started, I want to do a quick quiz. So when you look at data, there are 2 different kinds of data that you can think of. One is the quantitative, which is numerical data, and then the other is the qualitative or the categorical data, right? So when you say quantitative data, I want you to see that there are technically 2 different kinds of quantitative data, discrete and continuous. So I now encourage one of you to volunteer to give me a rough answer of what is the difference between discrete and continuous data. If you can give me an example, that would be great too. You can either unmute yourself, speak up, or you are also welcome to type the answer into the chat, whatever you like. Yes. Can you say that again? Yeah. So the question coming from classroom, I think one example that Aban is mentioning is that uh, he's talking about linear data sets. So for example, I think there are a couple of other examples, really good ones from Krishna and Swapnil. Those are also correct. Typically, signals or data that you can measure in a continuous, in a linear way is what we would call continuous data set. And discrete is where there are discrete counts that you can typically measure. So for example, I like the example that Krishna gives, which is analog signals versus digital. So analog is basically a continuous. You can think of it as an electric signal. So there's always some electrons flowing in, and you can measure how much current is in, and then is coming in. For example, that can be an analog signal, and then the digital component of that could be where you measure that electric current at a fixed periodicity, like every millisecond, and then that becomes a digitalized signal, right? So that's sort of you're discretizing it. But that is only discretization in time. But discrete can also mean what is the resolution at which you're measuring, which means typically when you measure current, you can go, which is measured in amperes, right? You can go from 0 amperes to, let's say, 10 amperes in your system. But between 0 and 10, there are infinite number of steps that you can measure, because the number of decimal points that you can add is what makes it continuous. But typically, you have a precision, which means you are going to ignore the lower parts of the decimal system. So let's say we just assume that we only value the 0.1 and above. So then that is where the quantitative data becomes a discrete data. So you're only measuring 0, 0.1, 0.2, 0.3, up till 1.10.0, right? So that is the sort of that's sort of the example of discretization. But again, the other example that Swapnil and Athar point out, right, which is a count of an object is a discrete data, right? And that is also a valid example. And yes, temperature is continuous. You can make it continuous, and length of cloth is also continuous. But typically, when we deal with continuous data, there's always something that we do to control the growth of data, right? We do something called rounding to control the number of decimal places that we value. And inevitably, because we process things in a digital system like a computer, we are always trying to create discrete numbers, and not we never compute in the real continuous number formats. And this will become evident because there's always going to be some prediction error whenever we do discretization, because you lose some small quantity of data, but that can add up as you go through the signal processing or the calculations. So that's a quick snapshot. So now I want some answers to talk about what is qualitative data or categorical data, and then what is the difference between nominal and ordinal. If you can give examples, that would also be great. Yeah. Correct. Ordinal is where you have qualitative data, but those can be organized in an order, which means if I say low, medium, high, it is already implied that they go in that order, right? When you say ascending. But when I say nominal, and I say tree, car, and cactus, there's no way that anybody can put it in an order that I will accept or someone will accept, right? So ordinal is ordered, nominal is not ordered, either because of the semantics of the language or the semantics of how the object is to those objects are to be perceived. So that is sort of the quick summary. Great job. Thanks for being very interactive. I think that's the focus of this bootcamp. So now I want to understand. Now you know about data. What does data set mean to you? What do you mean? What does data set mean to you? What is it? Compilation of data, right? So there's a step. So Aban's here say in the classroom says data set is a compilation of data. But now my question is, What do you mean by compilation? Can you give me an example of or describe what compilation means? Mhm. Yes. Right. Correct. Correct. So compilation is basically a collection of data or samples that are meant to convey a concept, right? In this case, in earlier case, it was the concept of a grocery basket or an inventory, and maybe in today's class, it's the housing data set, right? The California housing data set, which is a very famous, pretty famous toy data set. So data set is ideally a collection of data, which means there's always, when you talk about a data set, there's always some degree of uncertainty that has been managed. Because typically when you go measure data from the environment, right, through sensors or through you do a census, surveys, forms, typically you get a lot of error and misinformation baked into the collection process. But when you say it's a data set, you typically it is assumed that you have treated the data so that it is ingestible into a data science tool or into a algorithm for machine learning and things like that. So that's one of the distinctions. Data set is curated, which means it's not just a collection, it's also a curated collection of data, but that does not necessarily guarantee that it is fleshed out of all the bugs that it may offer, right? So we'll look at some of those pitfalls today, but also in the ethics of machine learning, we'll look at a lot of those factors that make learning models vulnerable to biases in the data set. Now, what is information? What is the difference between data and information? Yeah. Yeah. Can I maybe get other examples? Okay. Swapnil says knowledge or meaning of something or someone. Okay. That's a reasonable one, but I'm looking for a little bit more more thoughtful answer. Yeah. It can still be it can still be data, right? So I think Harsha says it's insights processed from data, right? That's exactly what information means, which means information typically means I provide you this information means you should be capable of acting within a reasonable bound, right? Which means if I just pump you sensor data all day, if I just keep reading numbers without giving you the context, that's raw data or data. But if I tell you this is the temperature that I measured in this classroom, then you have a little bit of context to figure out what you need to do, which is control the thermostat or open the windows, whatever it is, right? So information will give you a little bit of more context. Yeah, I'll repeat what is being said in the classroom. Yeah, thanks for pointing that out. So the thing that is being discussed in the classroom is what is the difference between information and data, right? So data can mean a lot of things. It can have some insight in it, but it is not apparent to the user when they look at the data. But information is where you have distilled the data and now you can understand what the data patterns are, what it means, right? And the information distillation process itself, you can think, is the focus of data science, which means data science helps you to take data, ingest it through a pipeline, take it through certain algorithms, certain decision-making steps, flowcharts, workflows, and at the end of it, you are now able to derive information or insights on what you can do further, right? That's the idea. So, so now let's go further, right? Typically, when you look at data science, it is a process, which means data science is not a single line of code or a single step in which if you understand that, you become a data scientist, right? Data science is a series of steps. And typically, each of those steps itself has become its own domain of expertise. And when somebody says they are a data scientist, they can be in any of these buckets or sub buckets, because that itself is a very, very deep subject. But we'll skim through some of those through the examples that we learn in this bootcamp. So if you see this example, this is actually a pretty good one I found online from Berkeley, and talks about the 5 steps of data science, right? Like five steps. Depending on what sources, there are people who give it more granularity or less granularity, but this is a reasonable definition of what I think we can start with. So the first step is capture, which means you have to figure out how to capture the data, right? That itself becomes part of the first phase of data science lifecycle. And then once you capture, now you have to figure out how to maintain the data, which means there's some curation, there's some processing, there's some architecture, there's intermixing with other disciplinary fields like systems, databases, XYZ. And then the third step is the processing, where you do some processing, which means you make some conclusions, you train a model, things like that. And then there is a fourth step, which is the analyze or the analysis step, where you now use the model and validate how the model is performing against new data. And that analysis is what is going to help us refine the algorithm. And finally, once you're happy with this capture, maintain, process, analyze cycle, you may actually do a subloop between these 4 cycles. And once you are fully confident that your model, either predictive or generative or diagnostic model, is working, that is when you communicate the outcomes, right? You communicate through visualizations, you communicate through tables, you communicate through reports, and so on, right? So there are all these aspects of life cycle. But finally, what I want to point to is this is a sort of iterative life cycle. There is no single step at which you can conclude that a model is fully done and you can say, you can walk out of the door saying I'm done. Data science is always iterative because you always tend to get new data in the real world scenario, and a model is never accurate, right? There's a very famous saying which says all models are wrong, but some models are believable or trustable, which means there's always a certain degree of error that any model will generate. But the focus of a data scientist is not to achieve perfection, but to achieve better clarity than the previous training, right? So that's the focus of data science lifecycle. Any questions before we move ahead?
Wait, you said that all models are wrong, but what if the model has 100% accuracy rate?
Correct. So typically, when in a machine learning model, they are probabilistic models, right? If a model is showing you 100% accuracy, there are 2 conclusions to make. One is you're modeling a subject that is too trivial, that the model is able to learn it. The other is the model is not learning, it's memorizing the content, which means there's something called memoization. We look at it in the traditional machine learning, but also in the advanced machine learning. But memoization is where it's a rote learning at that point, which means the model is not learning how to generalize its learning, but it is literally memorizing what the instruction is telling, which means if you attend this boot camp and you learn every word that I say, and at the end of the boot camp, if you're able to repeat every word successfully, but let's say if I give you a test that is out of the syllabus and it needs you to extend your imagination and you cannot do it, that is memoization, right? And that's a problem. It exists in humans, it also exists in algorithms. So there are 2 pitfalls there. One is either the data problem is too trivial, and you probably don't need a learning algorithm at that point. You can probably do with heuristic algorithms. And the other use case where you achieve 100% prediction accuracy is where you're probably training a model, but it is just memorizing what the data is, right? So, but there are different ways in which you can debug this problem. We'll definitely talk about all those things in the coming sessions. But that's a great question. I think that's a very solid question. Thanks for that. So before we go ahead, I would like to see if there are any other questions. I think I like the direction in which the interactions are going on. It really needs to be of this level. I want you to think through what I'm saying, and I want you to think through what you are thinking also, because that is the only way you can push your learning beyond into a space where now you can say, hey, I know the basics, I'm going to pick more advanced topics. So with that, please continue to engage. Please interrupt me at any point you have, but if you don't want to speak up, please do put it on the chat. If there are anything that comes up in the classroom, I will make sure to repeat it first before I provide the answer. So let's start with the exploratory data analysis. I think when I said intro to data science last session, when we started the Python project, you already touched one of the data science tools, and that was the Pandas, right? Pandas is a very popular data science tool that ties into the Python ecosystem, and it is very commonly used to analyze structured data, which means tabular data. And Pandas, I've been using Pandas for almost a decade now, and it's sort of you can say bread and butter for most people who even venture into data science or machine learning. And then visualization is part of storytelling, because humans just cannot understand tabular data. You may understand a table that has 20 rows of information, but if I throw you 1,000 lines of information, there's no way that you will comprehend. But if the same 1,000 lines can be visualized in a chart or in a plot, suddenly you have a comprehension of the concept, right? So that means data visualization or scientific visualization is integral to the science of data, to the data science. And we are going to do that today as well, right? For us to find insights, we cannot just let an algorithm do it, but we have to also bring a human element into it. And finally, you see a data set that is being imported here, but I did not use it finally because I found it had a little different attributes than what I preferred. So you can ignore the sklearn, we don't use it anymore. But in the next line where you say percentage matplotlib inline, it's basically an instruction to say whatever plots we generate, just print it as we go, right? And that's the goal there. So now what I will do is I will run the first one. It prints nothing. And then when I run the next code of line, I would like one of you to volunteer to go through the code, talk through what it means. Any volunteers for talking through the new cell, which is load the data set? Okay. We have a volunteer in the classroom. He will speak up. I will repeat what he said before we make progress. Okay, come on. Mm-hmm. Mm-hmm. Correct. Exit the program. Yeah. So Aban here gave an answer, which is there's a exception handling that is written here for loading the data set. What I am doing is, if you go to the left menu on your Google Colab, you see there is a directory icon, and within that there is a sample data, and then within that you can see there's a standard set of files that they provide for every Google Colab. That's basically a toy data set that they throw to all users so that they can get started without having to go import something else. So I just baked that into our classroom session today. So we're just going to import what is already available on Google Colab for every notebook. And read_CSV is basically a function within Pandas that allows you to read a comma-separated value, right? Does anyone have any questions on comma-separated values or what it means, or are you clear on it? Can I see a thumbs up if you're clear on it? Okay, perfect. So most people are clear on it. If you have questions still, please feel free to ping on the chat, and I'll keep track of that. But comma-separated value is what this data set is structured as. And in this case, there are two things that they give. As you can see, train and test. I just picked the training because that's typically the bigger data set. And then we will start doing some exploratory data analysis here to get started. So once I run this, it's obviously able to find it. So it does not print anything. There's no error. So it just runs, and you see a green tick mark that says it's done. So the next line of code, which is where I stored that data set, is cal_housing. What is this data type? Like, what is the data type that you end up with when you read through a Pandas? What is it called? We talked about it last session. What is it called? What is the table called in Pandas? No. It's called a data frame, right? So in Pandas, when you read tabular data, you end up with what is called a data frame. And right now, the data frame, the name of that data frame that we are talking about here in this context is cal_housing, right? That's the variable name. The data set is basically a complex data type, just like string or dictionary or integer and so on. So now the first thing I do is dot head, and then I pass it a number. Typically, you can leave it empty, and it typically prints the first 5 rows of data in that training sample. So as you know, in a comma separated value file, each row of information is equivalent to 1 data sample, right? And if I leave this empty, it typically prints 5 rows of data, right? Starting from index 0 to index 4. But in this case, I wanted to give you a little bit of context. You can add an integer here and print it, and now it prints 10 rows of data samples. And as you can see there, it gives you the row information on the sort of the y-axis, and on the column axis, you can see what those attributes are in the data set, right? So let's try to understand what we see here. So we see longitude, we see latitude. I'm sure that is understood. I'm not going to explain it unless you have questions. And then there's the housing median age. Can someone volunteer what that possibly means?
Like how old the house is, time since it was built.
Correct. Correct. How old the house is, yeah, since it was built. That's correct. And then total rooms and total bedrooms is basically, there's a big number. So I'm making an assumption here, right? But typically when you collect data, you will get additional information. But in this case, it probably is a representation of the number of rooms, and we cannot interpret it as 5,612 rooms in a house, right? So it's a representation of how rooms are going. It is basically a sum of total rooms that are in that longitude and latitude. And then among those total rooms, how many of those are total bedrooms? And then what is the population count there, right? 1,015 in that longitude and latitude. There's obviously discretization here, because how can 1,015 people live in one exact precision longitude and latitude? That's not possible. So there's always some error and assumption that we make in data science, and that is acceptable. And then there's number of households, which means if there's a population of 1,015, how many families or how many groups of how many households are available here? So in this case, it's 472. And what is median? What does median income mean in this context? Yes, Aban. Yeah. Aban says it's the average income of people living there. Can somebody point out to me what is the difference between average and median?
Average is like all of the income divided by the amount of income, or amount of instances of the income, but median is sort of the middle.
Correct. So typically, that's exactly the correct definition. But now my question to you is, why did they pick a median income and not the average income?
Average income can skew the data. So like if you have one guy that's super rich, he will skew the data of the actual average income.
Correct. That's a classic example, right? You say you live in the same zip code as Bill Gates. He's going to skew the average income, but he's not going to be able to skew the median income, because we are assuming there are lots of people in Bill Gates' zip code. And then because he's just an outlier, like you said, he is not going to have the biggest weightage when we calculate the median. So that's the correct answer. So in this case, that's why typically median is a good metric to go with. But there are exceptions where average or arithmetic average is still relevant. We'll talk about it later as we go through different problems. And then what do you mean? What does it mean by median house value?
The middle, like if you take all the houses values and like let's say a zip code, and you arrange them from lowest to greatest, the middle value.
Correct. So that's the right way to calculate the median of house value, right? So that basically tells you if you take an ordered list of all the house values in US dollars, maybe from Zillow or something else. In this case, this is from the data set. You can now calculate the median house value in that longitude and latitude. So this is a good example for us to understand what is happening here. So now let's proceed with the next steps, right? So in exploratory data analysis, the role of a data scientist is to think creatively, to be, intuitive, but also to be open to being proven wrong because the data says a different story. But in order for data to prove that you are right or wrong, you have to be willing to write some code, do some hypothesis, test it against it, and then see if you can visualize what you think is the right answer, right? And if that gets contradicted, you have to do that iterative search. That's the reason why it's called exploratory, which means you are now an explorator, and you have to keep your mind open to find the truth, right? So now what we do is, when we run this thing, calhousing dot columns, it's basically, I'm taking the pandas data frame, I'm finding out all the columns, and I'm now converting it into a Python list, and I'm storing it in a column underscore list variable, and then I'm going to print the column names. And then the number of rows is basically shape of zero is basically the dimension for the number of samples. So when I do dot shape square brackets 0, it basically gives me the number of rows of information in that data set. So when you run this, you should see the same column names that we saw earlier or discussed just now. And then when you look at the samples in data set, it's 17,000. Does everyone see the same thing when they run it? Okay. Perfect. So that means we all have the same data set, and Google is not sending me a bigger data set or smaller data set than the rest of you. So we're good. So then data.info, right? So typically a data scientist needs something to start with. So you can ask pandas to describe, give you some information, but you can also say cal_housing.describe. These are sort of built-in functions to do a quick description and information. So when you do the data info, what you can see that it says this is a data frame from pandas class, data frame class from pandas. And then it says the range index has 17,000 entries, which means index going from 0 to 16,999. And then it says total data columns are 9. And then can you help me understand what it means by non-null count? Can anyone take a guess? Any guesses so far? Yeah. So that's correct. So there are, what it says is there are no null values. So sometimes when you take a data set, there could be values that were not captured successfully. So the practice there would be to call something which says null or not a number or something else. And in this case, this data set is actually clean, which means there are no cells in your data frame which are not explainable as a number or as either as a qualitative or a quantitative number, right? So this data set is already clean. We don't have to worry about figuring out how to deal with the null values. So we'll talk a little bit more about dealing with null values in the next class. But for now, that's the goal here. And you can see it talks about the data type. So in this case, it's reading all of it in full float 64, and memory usage is 1.2 megabytes, and that's the data info. Then there's the data description, which means it goes through each column and it calculates count, which is the number of occurrences of value or samples in that column. And you should see 17,000 across the board. And then mean is the arithmetic mean that we just discussed. Then 50% is the median, right? In this case. And then there's the 25th percentile or the 75th percentile. So remember, 50th percentile means it's referring to the median. Min is the minimum value there. Max is the maximum value, right? Like typical basic, what you call descriptive statistics, right? This is 101 for, I don't know, class 7 or grade 7 or grade 6, right? So this tells you a quick snapshot, right? So now my question to you, right, is, let's say we look at median income, right? So what does median income tell you here? Do you think there are outliers, or do you think there are no outliers? 15 is probably outlier. That's correct, Harsha. So that is correct. So what is happening here is um, when we go through this column, right, median income column, what we notice is the max value is 15, right? But I want to get a little bit of more context, potentially answer from Harsha or someone else, which is, how did you come to a conclusion that that is an outlier? Is there some other information that you can look into and then say why it is likely an outlier? Standard deviation. That's a great answer. So Krishna, if you can unmute yourselves and help us understand what you mean by standard deviation. That's a good answer, but I want to understand the context there. That's correct. 50% and max is extremely high. But when you say extremely high, we are using our judgment. But if we were to talk about it in the perspective of science, we're talking about standard deviation, right? Like that's what Krishna mentioned, which is, so from the median, right? How many times do we have to add standard deviation to get to the max, right? So typically, when you look at standard deviation is also called sigma, right? So if you say 3 sigma, typically 3 sigma covers 99% of the cases in the distribution. And we are assuming, obviously, that this is a normal distribution. But then, given that 15 looks abnormally high relative to both the median and the standard deviation that we are measuring, that is how we concluded it's a large number. So Harsha is correct, but it's just that there's a little bit of a statistical way of interpreting that, which will help us draw the similar conclusion, right? So it's so that's the fine line between data science, which means we have to base it through metrics that can be explained. Exactly. So there are different ways to calculate max outliers. I think Rohan is pushing some sort of a formula that we see here. That is definitely possible. So there are different ways to figure out outliers. So now, what do we see here when we look at the median house value? Do we see a similar story here? We do, right? So when we look at both the median income and the median house value, we typically see that the mean is much higher than the median. And that tells us that there's probably somebody who's at the high end of the earning bracket who is distorting the view of the mean. And similarly, there's somebody with a bigger house or something like that who is also distorting the view of the mean, right? So that's the same conclusion that we drew earlier, right? So that's good. So now, moving forward, let's go to the univariate analysis, right? So univariate analysis is a statistical term to say we need to look at each attribute, which means each column on its own strength to see how the distribution looks, right? And a typical way of visualizing distribution is what we call histogram, which means you take continuous sample of data, in this case 17,000 samples for each of the under each column, but then we cannot plot all the 17,000, makes it just chaotic. So instead you say I will bucket small ranges and you will group all the data, and instead you will project the y-axis as the count of number of samples that you found within that bucket, and that is what generates the histogram. So can anyone help me with what is this term where you see these two peaks? What is it called? Has anyone come across the term, how this is called in statistics? What is it? No, it's called multimodal, right? So in this case, it is bimodal data, which means there are sort of two concentrations of data in the histogram, right? There's a bimodality is what you say. But then if I go further down, when I, let's say, go to median income, it follows what is called the normal distribution, right? So there's a unimodality, which means there's a single median, and then there's a standard deviation, and you see this beautiful looking curve. Yes, Swapnil is bringing up a good point, which means there's a skew. Now, what does a skew mean is, typically we expect the median income to be equally distributed around the median, which means the shape of the histogram should be sort of symmetric across the median. But in this case, what Swapnil is pointing out is the shape looks sort of weird on either edges, which means if you fold it in half, you don't really see the same rise and fall. That's correct. So there's some skew, and there could be different reasons for the skew in the data set, right? And that is also one of the things that we have to be wary of, and that is going to be discussed again when we talk about the ethics of practicing data science. You have to be perceptive to all these small things that are baked into the data set, without which, if we draw some conclusion, it is not going to be truthful, right? It can be misleading. So that's the risk of data science that we have to deal with. That's a good point. Yeah, thanks, Swapnil, for pointing that out. So similarly, you see in the median house value, you see the same thing, right? Which is the skew has a weird thing, and then there's some outliers in the median house value for whatever reason. So all those things are typically what we encounter in real world data sets. Now, if we go and visualize the data based on the location, right? So I just want to visualize the data because this says Cal housing, right? So, and it gives me longitude and latitude. So obviously I see this weird looking shape. What does this remind you of? Yeah, is the map of the state of California. And why do we see concentrations of data? What does that mean? Correct. But basically those are like city centers or rural centers. And that basically is telling you that there's no uniform collection of data possible because people don't live at every latitude, longitude intersection, right? That's the idea here. And now, but this data is not going to give us anything beyond that, right? So now we want to add another dimensionality here, even still within the context of univariate analysis. So what I do is I take the same thing, but then I say alpha equal to 0.1. Alpha is basically setting the transparency for each scatter point that we plot. And then I say color it by the cal underscore housing of population. So this is a way of addressing the column. And I want you to think about what I'm doing here, right? I want you to think about it. I want to hear some good answers there. You're feel free to change this and manipulate and figure out why I'm doing that. And then CMap is basically the color map, and I'm saying use reds. And when I run this, obviously you can see I am plotting the same data that I showed earlier, but now wherever the population density is higher, right? Wherever the population numbers, the absolute numbers are higher, not density, absolute numbers are higher, I am now plotting them in brighter shades of red. So now my question is still, what am I doing here by doing star 0.1? What did star mean when we discussed Python in the very first session? To the power of, it's exponentiation, right? But now my question is, why am I doing exponentiation of 0.1? Why am I not using the actual value to color? No, the reason I'm doing that is, let me walk you through that live, okay? So when I remove this, right? And when I visualize, this is how I see the data, right? Especially with the alpha. It is super hard for me to see the colors on any day. But now, what happens if I just add it by 10? When I add it by 10, what happens? Nothing changes. Why is it that nothing changes when I multiply it by 10? Because I'm just, if you have heard the term clamping in signals, I'm just clamping the whole thing by an order, and I still end up with the same distribution. The color, the relative color differences are not going to show up. But when I do exponentiation, what does happen? What is the exponent of 0.99 to the power 2 versus 1 to the power 2. There's a huge difference, right? Even though the difference between 0.99 and 1.0 is just 0.01, when you do the exponentiation, you're blowing up the error, right? So now if I do exponentiation by, let's say, an integer, it gets worse, right? So what I did is, by exploratory analysis, I figured out if I do 0.1, I can now make it explicitly different, because now instead of taking a square like a to the power 10, I'm actually doing a square root, right? And this helps me to visualize the areas where there is higher population density. And this is one of the two things that's the reason why I call this, you need to be creative, is you have to make sure you can derive insights that can be understood by people who see your reports, see your plots, and you should be able to explain why you did it and why it does not change the nature of the data, right? So in this case, I'm not changing the nature of the data, I'm just showing it in a way where I can visualize it better, right? So that's the idea. Now, similarly, we'll see if there are any questions. Are we good so far? Can we see the thumbs up? Okay, perfect. So we'll make a little bit of faster progress now. I think we're a little slow right now. So we'll do the bivariate analysis, which is, now we want to see how do two factors come into play at the same time, right? So now what I do is, I say the size, which is S equal to Cal housing of median income, exponentiated by 2, to basically to the square of 2, square to the power 2, and then exponent to the power 2, sorry, and then label is a median income, and then I say color is still median house value, and then I say give me this color, and I say show me the color bar true, and then when I run this, right, obviously this is giving me this plot. It's still plotting the map, but now I want you to help me understand what I am trying to tell here. Who can volunteer? Let's all walk through. I'm not expecting perfect answers. Yes, Krishna Karthik has come to some conclusion, which he says LA and SF are expensive. So probably Bay Area and LA are super expensive. Probably San Diego and probably somewhere in Santa Cruz or whatever, Monterey, right? So probably that's Carmel by the Sea, if you've been there. It's pretty expensive neighborhood. So what you see here is, we plotted latitude and longitude, nothing changes there. But then we are saying, make the size equivalent to household median income, right? Which means if you go to Bay Area and San Diego or LA, it means the median income is much higher, right? That tells you that the jobs there are probably paying higher for whatever reason, right? Nature of job, nature of the market, XYZ, there are lots of factors in play. But then, what is the color telling you? The color is telling us, what is the color telling us? Yeah. Color. Exactly. So the color that we picked was from median house value. So that is telling you, in high income regions, typically you will find more expensive houses, right? And it's not surprising why people say Bay Area is expensive. But they're getting paid more dollars, but they're also spending more dollars for the same square footage or for the same configuration of the house, right? And that's economics, markets at play. But this is a good way to explain those behaviors through data. And a data scientist's job is not done by just running code or writing algorithms to analyze data. A data scientist's job is to tell a story, right? End of the day, you are a storyteller, but you're not telling fiction, you're telling from facts, right? That's the difference. So now I think we are good. Any questions so far, please post it. Yeah, that's another good. Darker is more expensive home, or those brighter colors mean more expensive homes, and then high and low income ranges. So you can now do lots of conclusion, lots of analysis based on this. People can derive insights. And then you can also see where we see Central Valley, right? Like that is probably roughly where Sacramento is located. Again, you see there's a cluster of bigger, so median houses still go up in Sacramento area, but the sort of the median house value does not go as high as Bay Area, right? And that is known by us based on general conversations that we have with people who live there or live here, right? So that's the idea. And then now we do bivariate, where we try to explore what is called a correlation matrix, right? Correlation matrix is, in a simple way, there are different ways to do correlation, but in this context, what we mean by correlation is, if I have one column and if I have a second column, do they have a linear relationship in this context? Which means if I push the knob up on one column, does the values in the other column also go up simultaneously? If it goes simultaneously up, then it means it is positively correlated. And in this case, based on the graph that you see here on the color bar, positive correlations will be shown in shades of red, which means if you have one correlation one, it is fully correlated. And then there's negative correlation, which means if something goes up and the other column comes down, it is negative correlation. So that's basically in blue. Okay, we have a question here. Oh, okay. So let's see how it is running for me. Yeah, I think if it is not running for you, maybe you have to import Seaborn. So let me share the snippet. Yeah. Yeah, I probably had it. I don't know how my thing is still running, even though I seem to have deleted it. Do we see the same? Yeah, import Seaborn as SNS. I think that should hopefully fix it. Let me know if it still doesn't fix it. Is it working? Okay. So probably there's some weird caching thing that is happening on my notebook that it somehow think, okay, maybe I did not restart the notebook, so it's still thinking it knows what is SNS. Okay. So hopefully everyone, please look at the good comment from Rohan. He says add this import, so you can add it at the start of the script like I did. So I just went up here and then I added it here. And what I'll do is I'll just quickly commit it also, so that next time you pull it, you will be able to find it. Sorry, I have too many repos. Okay, so I think we are good so far. So this classroom is definitely more intense than what you may have expected, because there's a lot of concept. So, and there's some exercises that we'll try to do now quickly. If we don't walk them through all of them, we will you will continue working on it. Post questions either preferably on Discord, if not by email. If you're still stuck, let us know and we'll help you out. So just to give you a quick context, right? This is the California latitude longitude map, right? And you can see these latitudes here and longitudes marked vertically. And then you can see a interesting thing that I don't know if you had observed. California has this one latitude line. If you basically cut California there, you will split no county by half or by any portion, right? If you basically convert this into two states, I'm not proposing that, but I'm just saying hypothetically, if we split it at that line, you are basically creating you're not splitting any counties or taking any land away from them. So we'll take that assumption, and that's sort of hinted at here, which is now I want you to assume that 35.79 degree north latitude is the split for north and south. So now I want you to do the same data analysis that we discussed so far, write code by splitting the data set to northern and southern California, which means you'll take the data frame that you have, and I want you to create two sub data frames based on this condition, right? So now I want you to start thinking of how you would do that, and then we'll come back to that. How do you split a data set? I know you may not know how to write the code yet, but I want you to maybe unmute or put on the chat how you would do this. Give me the sort of the pseudo code of how you would do it. I'm not expecting the pandas code yet. How would you do it? Let's see. I'm going to try writing code live. I'm going to take some snippets of code I have on my site. Okay, Swapnil, you have please go ahead.
This might not be the most efficient, but I think what you could do is like you can go through each like data point, so each latitude longitude line, and just check if the latitude is greater than 35, then you make it north, and then if it's less than or equal to, then you can make it south.
Correct. That's one of the ways to do it. That's actually a good way. But the beauty of pandas data frame is parallelization, which means it gives inherent parallelism, which means you don't have to go in a loopy way through all the 17,000 rows in this data set. So instead, what we'll do is we will say cal, we'll do this ncal, which is North Cal housing, right? And we'll say scal housing. Okay, and we define two variables here, right? And now this is going to be, it's obviously reading things. Google Colab has integrated a smart feature, so it is now interpreting based on the hint. It now knows that it has to be based on cal underscore housing, where I'm saying cal underscore housing of what is the we are based on the latitude, right? Latitude being greater than 35.79, right? And in this case, that we may have to do an equal just to be sure. And then what we do is South Cal is going to be less than this, so that we can probably get the right values. So now let's see North Cal underscore housing dot. How did we get the number of rows of information? So we go back. We don't have to memorize, but we can go back to this and say, give me the info, right? So I can just say, give me the info here, right? And then I can say, so, right. Okay. So let's see what happens when we run this. So when we run this, we get these two numbers. 7264 is the North California dataset, and South California dataset has 9736. Now, can we quickly add it and know whether that is correct? Can somebody do the quick math and tell me if that number adds up to the actual data points here? So basically 7264 plus 9736, right? So it is 17,000. And the only way we can ensure that is to make sure that there are no exclusions done here. And for that reason, I am being a little biased to North Cal, and I'm saying you can also include data points that are equal to that latitude and longitude. So I'm giving them a little bit of a boost, given that we are in Northern California. But the story is it's not going to help them, because what we see here is Northern California part of the data set has 7,264 data points versus 9,736 data points for the South Cal, right? So which is fine. So that tells you there's some imbalance in the data collection mechanism. So maybe the creators of data set ended up with more data from Southern California, so they seem to have sampled it unequally, right? And that does not mean they're wrong. That just means that since I'm splitting it based on my own assumption of where the north-south split is, I am ending up with a with this behavior. So are we good with where we are? Is everyone? Swapnil, I see a question. Why are we doing 2 cal_housing? So, okay. So are you talking about this one? Is that correct? Yes. Okay. So the reason why we are doing it is, let me walk you through the syntax here, right? So where I am saying cal housing of latitude, right? I'm saying, look at this column and return all the values that are greater than or equal to 35.79, right? So it is basically giving me an object, right? But then I'm saying, take all those indexes from the original cal housing data set and now assign it to this new data set, data frame. Sorry, where I said data set, it means data frame. So essentially what this is doing is, out of this is the condition to filter, and that condition needs to be applied to the cal_housing data set. So here cal_housing is only used because we need to tell it where to find the latitude information. Whereas here we are actually referring to the data frame and telling filter it by this condition. Is that clear? Can I see a thumbs up? Okay, perfect. So we will continue. Okay, so now what is the next part? So we need to do the above analysis, right? So how do we do the above analysis quickly? So maybe what I will do is I will copy my favorite plot here, right? Let's say, would this change? This would not change, right? This would not change because I will only end up creating 2 things that would just get split into 2 separate images. So I'll not redo it. But this will definitely change. The bivariate analysis is going to change because when we are doing correlation matrix, now we are ending up with 2 separate data sets. So what I will do is I'll create 2 separate cells here underneath. And then I will say this is correlation matrix for NorCal, and this is correlation matrix for SouthCal, is SoCal, right? And then instead of saying wherever it says cal housing, I'm going to replace it with NorthCal, and then NorthCal, and that's it. And here I will say SouthCal, and SouthCal. And then I can say SoCal heat map, and here I can say NorCal heat map, and then I go and run it. So now we are going to look at some interesting behaviors here, right? So now I want you to look at the 2 correlation matrix that we have, and tell me whether if you think that they are giving us the same information, give me a thumbs up. Or if they're going to give us the same conclusion, give me a thumbs up. Okay, so nobody gave a thumbs up. That's the right answer, which means you are seeing different values in the 2 correlation matrix, right? And that tells you a story, right? Obviously, the diagonal column that you see here is going to be 1 always, because you're basically comparing the variable to itself. That's not bivariate analysis. But now, let's say we make some analysis here, right? So what happens when we take the median income and then we compare how it correlates to the median house value, right? In this case, in NorthCal, median income correlates to median house value, right, by 0.72. So it's still positive correlation, but it is not correlation 1, which means there's some discrepancy there in how they correlate, or some gaps. And then when we look at SouthCal, it actually is lower, right? Which means it is not as highly correlated relative to NorthCal, which means in Southern California, it is going to be tougher to say using the same model to make a conclusion that a specific median income can imply that they may be in a house that has a specific median value, right? So that essentially means the data, when we split it, is now showing some unique behaviors that maybe is tied to some factors. We do not know what those are. And the goal of a data scientist is not to explain why that may be, but the goal of data scientists in our context is to point out that they are seeing this discrepancy. Why that difference exists is now what a domain expert on housing and economics and social sciences may have to think about and come with a hypothesis or an experiment to test it out. But what a data scientist will do in this context is to say, when I do this analysis, I'm seeing this behavior, and the insight that you're providing is a question to say, why does this happen, right? So that's one of the ways. But let's say you are a domain expert who is now learning data science. So let's say you are a social scientist who is also a part-time data scientist. Maybe you will be able to explain why we see this difference, right? Maybe you have a hypothesis or you have some other data to explain why this happens. So this is the reason I'm talking to you through this is to help you illustrate that data science is not the only way to arrive at conclusions. Data science, in a lot of cases, may open up the Pandora's box of questions, but end of the day, a domain expert will be more fine-tuned to make a more understandable conclusion or more actionable conclusion. So the goal for any data scientist is to develop two things. One is expertise on the data science, but again, expertise on the function, as I point out here, is also equally important for you to explain why you see this difference when you split the data set. So this is basically one example I wanted to highlight. So now I think Swapnil had a question. Swapnil, is that answered? Can I see a thumbs up, or you're still confused? You're good. Okay, so that's good. So what the question was, let me summarize it for everyone, is he's asking why we cannot just say cal housing of latitude greater than. The reason is latitude in single quotes is not a variable that Python can interpret. So we have to first say, where is this latitude coming? And that's the reason why we say cal housing of latitude should be greater than this. And then that is the condition to filter cal housing. That's the reason why we end up with this weird construct which says cal housing of cal housing. So in this case, cal housing of latitude is referring to the column and not just the data set. And together it becomes the condition that gets applied to the data set to filter the rows that are satisfying that condition, and that gets assigned to the new data frame variable called ncal or scal housing, right? So that's the idea. So now the next one is analyze the correlation between median income and median house value, right? So who wants to volunteer, maybe screen share and walk through the solution? It's okay to fail or not know the syntax, but the goal here is that we will collectively make an attempt to solve that. Who wants to volunteer? Anybody from classroom or online is fine. Okay, so that's fine. If we are not sure what we are doing, let me go through this again. Okay. So now the question. Okay, maybe help me understand what I am trying to ask you here. Like, what do I mean by analyze the correlation between median income and median house value further? What do I imply by further? How will you? What is the answer that comes to you? Yeah, bivariate analysis. That's the correct answer. But what am I asking you to do? What appears in your mind when I mention the word further in this context? How can we do bivariate analysis? What are the other ways to visualize this? Maybe a table, but how will you visualize 17,000 rows of information? How do you do that? So one hint I want to give you is, let's do a scatter plot, right? So now how can we do a scatter plot of these two values? We just go back to where we did the scatter plot, right? Like we did a scatter plot here at the start, right? So what I want you to do is start from the simple scatter plot that we did. Like copy this, right? And then we go here, we paste it here, right? And what I'm asking you to do is plot, scatter, and the inputs are going to be median income and the y-axis median, sorry, what happened? Median house value. And when we run this, we see this behavior, right? So now I want us to think what could be happening here. Can anyone describe what we see here? Yes, we can do a heat map, but in this case, we'll start with just the bivariate, which means we'll only take the two variables. Yes, right now we are basically plotting a scatter plot, and that is essentially correct. What Krishna says is it's a plot of latitude versus longitude, and in a scatter plot, which means we plot each individual data point for the two x and y values, and it's a direct correlation, visualization of the correlation, right? So when the correlation was done earlier, right, which means when the correlation was done for median income versus median house value to come at this number in the heat map, right, what it did essentially was it tried to fit a line to say what is the predictive linear regression model that can be done in a way where I can take median income as an input and try to predict what is the median house value, right? But what we also observe is, if I were to draw a line here, it is not always going to be accurate, right? Which means, given that this is the nature of real world data, for a given median income, there's a huge distribution of median house value, which means if somebody were guaranteed a median income of 4, whatever that means, right, we will see that we cannot really predict super accurately or super perfectly what kind of house they will use, right? Or what kind of median house value will they possess. The reason is the noise that you see here for a given median income, the variance that you see here is because we are implying that there are other factors fundamentally that help explain this problem, right? Which means this problem of predicting median house value cannot be based just on median income. It is a multivariate analysis, which means we need to consider more variables to come explain this linear trend, right? And now what are those linear variables? We will definitely look at those in the next session, right? Which is where we start playing with some of the ethics of data science. But again, in the third session, which is the traditional machine learning, where we start fitting linear regression models for multivariate analysis, right? So those are the steps that we'll have to take. Now, what I wanted to illustrate here is univariate, bivariate can give us some information, but what we are seeing is it is not enough to help explain the whole data, right? Which means this data is much more complex than what we can visualize in a graph. But using a machine learning algorithms, now we can build an algorithm. We can hold back a part of this data set. We can create a hypothesis saying, if we build this model, train it on a sample data set called a training data set, we will be able to use the test data set, which is also present in the same contents folder, and test if our model is now doing better, because now it is a multivariate prediction. It's a multiple variable regression model and not a single or a two variable regression model, right? So we'll look at that. So before we go there, any other questions so far? Can I get a thumbs up to make sure that you are all good with what we have discussed so far. Okay, so in the interest of time, we have to conclude in the next 3 to 4 minutes. I will not be going through classroom exercises 3 and 4, 5, but I will just describe what needs to be done. And I hope that you can spend some time beyond the classroom to actually write code and visualize and write some conclusions. And these are all based on things that we have discussed. Maybe there are some small concepts that you may have to learn, but internet is a very great resource for that. So classroom exercise 3 is asking you how many top 5 percenters, right? 5%. 5%ers which is use median income, live in homes worth less than 180K. So I'm saying if you take the top 5% of the population based on the median income, how many of them by count, which means I'm asking you to give me a count of how many of those top 5 percenters live in homes lower than 180K. And you may ask, why? How did I pick 180K? I'm a data scientist, so I need to base it on some hypothesis. So I went to the median house value, and I saw that the median value is $180,000, right? Based on what I see here. So I'm now trying to find out if you find a top 5 percenter who is living in less than 180K, then maybe that tells something about where they live or what they do or why and things like that, right? So that's the sort of the analysis that we are trying to do here. And then I want you to say how many top 5 percenters live in North versus South. That's again a simple count. Same thing with how many bottom 5 percenters now live in a home that is worth greater than 180K, right? Now we're saying, is that also something that we can figure out? Maybe there's some weird behavior that we see there. And similarly, how many bottom 5 percenters live in Northern versus Southern California, right? So these are all simple things that you can walk through. And then the fourth exercise is, do you observe more new homes in Northern or Southern California? Which means now we are going to look at the different column, which is the median house age. And I'm saying filter it by less than 10 years. And then if it is less than 10 years, you can tag that as a new home. And now I want you to figure out if the data set tells you that there are more new homes in Northern or Southern California. But this question is ambiguous. It is not technically asking you to just count the number of new homes. Maybe what we have to calculate is how many percentage of new homes exist in Northern California versus how many percentage of new homes exist in Southern California, right? Which means within that less than 10-year category. That's the exercise here. And then the fifth exercise is, now go figure out how to import an external data set and try to do a visualization of the time series data in this data set. In this case, it's the COVID-19 equity metrics, which talks about how different races of people in California were affected by different rates of COVID-19 tests administered, COVID-19 cases, COVID-19 deaths, and so on, to see if there are some interesting behaviors that you see attributable to race or something else, right? Like where they are located and things like that. So the goal of a data scientist is to understand the truth in data and question observations, or surface those observations, surface those insights for experts who are domain experts to then find out what is the action that they need to take based on that data, right? So the goal of a data scientist is not to worry about the exploratory data analysis. The goal of a data scientist is to figure out how to do it in a way where you can derive insights without getting subject to bias and ethics in the very first step, right? So that's the goal. So please go through the remaining exercises. I think it's going to be a very interesting set of exercises for you to practice data science. And this is going to tie very closely into what we'll do in the next session, which means we will talk a little bit about what could be wrong things that you can do as a data scientist, either intentionally, hopefully not, but even unintentionally, you can be making mistakes. And how do we, what are the tools that we can use to make sure that we don't make mistakes as a data scientist. And that ties into the ethics of practicing machine learning. That is not going to be a lecture of philosophy of ethics, but it's going to be how to practice the ethics of data science in code and in hands-on effort. So with that, I want to conclude today's session. We're past the minute, but I think that concludes the session, so we can stop recording. If there are any questions, we can